The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Opera, that's a good one. That's good. It was opera, yes. What opera? No, it wasn't Wagner. But it's a good guess. It's certainly Verismo style, way over the top. That was Maria Callas singing La Mamma Morta from Andrea Chenier, which was written in 1895 and premiered in the spring of 1896, exactly at the time when the world was going nuts over this mysterious form of radiation that could see inside the human body. So I thought that was a good match. Things best in class. That's Maria Callas. This is opera for those of you who don't like opera. Listen to this. This, by the way, some of you may recognize if you saw the movie Philadelphia. This is the piece that's playing when the Tom Hanks character visits the loft of the, the Denzel Washington character visits the loft of the Tom Hanks character. And this is playing. It's a fantastic piece, way over the top. And this is Maria Callas, who was the woman that restored melodrama to opera. It's fantastic. So go and listen to it. Enjoy it. And there's Bertha Röntgen's hand, reminding us of the fact that you always irradiate the one you love. Okay, so I have a few announcements. Next week, a week from today, there will be no lecture. Instead, celebration of learning. Celebration number 2, Wednesday the 27th, coverage through today's lecture. We'll go through the generation of X-rays, but we won't touch anything to do with the use of X-rays and indexing crystals, Bragg's law, any of that stuff. So anything we talk about today, I think, is fair game. And we'll go back to the early part. So I think last time we said up until the 22nd. So I'm going to say the 22nd is fair game. We started talking about the properties of ionic compounds and electron transfer, octet stability. So we'll go through all of these. We've covered a fair bit of ground, and we'll end with X-ray spectra, but not Bragg's law. Okay? So second thing, I want to remind people that we've been getting, I had a staff meeting yesterday, and many of my recitation instructors said that some of you are puzzled to learn that there's more than one book. The text is, in fact, 3 volumes. And right now, the X-ray readings are coming from this volume here called the Course Supplement. So you need to be aware of that, and also some of the best materials in the archive notes on the web. And also, all of these images that I show, they get posted as well. So some of you are feverishly taking notes, and that's good. But if you miss something, you can go and take it off the website as well. Last point that came out of the staff meeting last night, a number of people are becoming tardy about taking the weekly quizzes. You're allowed to miss the weekly quiz for either health reasons or some crisis in the family, but not because you just decided to sleep in or you decided you'd like to take it at a later time. So I'm giving the TA's discretion to deny you the right to take a makeup unless it's proper. I'm not asking that you come with a medical certificate or anything, but we'll take you on your honor. But I do expect you to take those tests when they're offered. If you can't take it on the day, you can take a makeup up to 1 week. After that, we want to close the books on it. And we're not going to allow you, as is the practice in other classes, to throw away your bottom 2 or 3 scores. If you don't take them, you'll get zeros, and that gets averaged into your homework grade. You know, I want you to have the discipline of weekly homework and weekly homework quizzes. So I know that recitation instructors are announcing this, but I want you to hear it from me as well. So it's only good. It's good for your mental health to take those tests, you know. It keeps you sharp. Okay. So last day we talked about Röntgen and the discovery of X-rays. Röntgen was working in this laboratory studying gas discharge tubes, and his special take was high voltage and low pressure. And under these circumstances, he was generating unbeknownst to him until the night of November 8th, 1895, photons of a wavelength approximately 1 angstrom. And we looked at the relevant physics and concluded that we could explain the generation of X-rays by this energy level diagram, which is the energy level diagram of the target. This is the anode. Remember, the gas discharge tube has a cathode, which is charged negatively, and electrons are made to boil off the cathode, accelerate from rest, and they crash into the anode over here. And we think when these electrons crash into the anode, they cause a set of operations that ultimately result in the emission of photons in the X region of the spectrum. So this is the energy levels of the element here in the target. And we reasoned that these incident electrons coming with kinetic energy imparted by acceleration voltages in the range of tens of thousands of volts have enough energy to come in and actually dislodge, come in and dislodge inner shell electrons. And in the extreme, even n equals 1, K shell electrons. And when that happens, there's vacancies that invite a cascade. So we have a cascade of electrons in the anode target from higher levels down to lower levels. And as you know, going back to the early part of 3091, when electrons move from high energy to low energy, photons are emitted, and these photons are the source of the X-rays. These are the X-rays here. So we saw that if we had a vacancy in the K shell, we could get electron moving from L shell down to K shell, and such a photon was termed a K alpha photon. K because the photon came from an electron cascade into the K shell, alpha because it came from one shell above K. There's a slight chance that the that the electron may fall from n equals 3 down to n equals 1. That's a greater energy difference, and we will get a K photon, but K beta. K beta indicating that the photon fell to K from 2 levels up. And I even, just to complete the picture, I put K gamma. Well, if there's vacancies in the K shell, if we have enough energy to dislodge electrons from K shell, we certainly have enough energy to dislodge electrons from L shell. Vacancy here would invite a cascade from n equals 3 to n equals 2. This would be L, alpha, because L is the destination shell. Alpha meaning you came from one shell above. In the event that you fall from 2 shells above, n equals 4 down to n equals 2, this will be an L beta photon. And thus was the way we left it last day. And the last thing was that the instant energy values here, and therefore the instant wavelengths, are determined by the chemical identity of the target. If I change the composition of the target, I have a different internal energy structure, and I'll get a different set of emissions. So that's what was left at the end of last day. So now the question is there a quantitative relationship between any of this? Specifically, is there a quantitative relationship between the chemical identity of the target and any of these wavelengths that are observed? And the answer is yes. And for that, we go back to Manchester and the person of a young graduate student by the name of Henry Moseley. Henry Moseley. He was a graduate student working under Rutherford, 1913, 1914. And he was conducting a study, what we call a systematic study. Systematic. For those of you who intend to become graduate students, I want to let you know this is a very dangerous word. What systematic means, it's polite talk for tons and tons of measurements. Systematic. His systematic study was to take the X-ray generator and change the chemical identity of the target. And he conducted a study of no fewer than 38 elements. 38 elements, systematically changing the chemical identity of the target and measuring the spectrum, the emission spectrum for 38 elements. He started as low as aluminum and went all the way up to gold, stopping 38 places along the way. And he measured the wavelengths of these X-rays, and he found a pattern. He found a pattern. What he found was that as the molecular weight, or as the atomics, and we're just dealing with elements, as the atomic weight rose, the wavelengths fell. So I'm comparing apples and apples. So let's compare all of the K alpha lines. So the lambda K alpha would fall as the heavier and heavier elements were used. And here's the plate from one of his papers. This is a beautiful piece of work. These are the photographic plates along the lines of the Balmer series, only this is from the X region of the spectrum. So here's calcium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and brass. Here's where he's going. There's calcium. Didn't have scandium. It was too rare and still to this day very, very expensive. So now he's moving across the transition metals. He gets to copper, and he can't use zinc for reasons I'm going to show you very shortly, namely that the energy in that tube is so high that he's going to melt the zinc. So he says, instead, I'll use brass, which is an alloy of copper and zinc. And so this is the data from his study. And so here's the first line of the first page of the paper. The author intends to make a general survey of the principal types of high-frequency radiation, examine the spectra of a few elements in greater detail. The results already obtained show that such data have an important bearing on the question of the internal structure of the atom and further support the views of Rutherford and of Bohr. This is what he's putting up here for us. And what I want to show is that when he took his results, this is what he found. He tried to get a better functionality of this relationship between wavelengths and atomic weights. And here's what he found worked best. He found that if he plotted not the wavelength but the wave number, which we've seen before, the wave number as a function of proton number, and in fact the square of the proton number, he got a linear relationship. So, and let's just say this would be L alpha, L beta, K alpha, K beta. And let's say you're at copper. So copper would be 29 squared. So he would get data for the L alpha line of copper, the L beta line of copper, K alpha line of copper, K beta line of copper. He might not get all four lines for every element, but he would take sets of data and plot them out, and he found that if he plotted the reciprocal of the wavelength versus the square of the proton number, the points lay on a line. So over here would be aluminum, and over here would be gold. Over here would be gold. And this was extremely important. This changed so much, because look at what he's able to conclude here. Let's read his paper here. We have here a proof that there is in the atom a fundamental quantity which increases by regular steps as we pass from one element to the next. This quantity can only be the charge on the central positive nucleus, of the existence of which we have already definite proof. And remember, when Mendeleev enunciated the law of periodicity, he said that the properties of the elements are a function of the atomic weight. A function of the atomic weight. And people were perplexed by the fact that potassium is less massive than argon. But no one would put argon under sodium. But Mendeleev's law is that you arrange things by atomic mass. Cobalt and nickel are reversed. What to do? Here's Moseley. We are therefore led by experiment to view that N, his capital N is what we call proton number, is the same as the number of the place occupied by the element in the periodic system. This atomic number, he's coining the term, this atomic number is then for hydrogen 1, for helium 2, for lithium 3, for calcium 20, for zinc 30, etc. We can confidently predict that in a few cases in which the order of the atomic weights A clashes with the atomic order of the periodic system, the chemical properties are governed by N, while A itself probably a complicated function of N. This is brilliant. This is a graduate student in 1913. correcting Mendeleev. So, what are the implications? What are the implications? So this proton number, we're now going to give it its due. We're going to call it Z, the atomic number. This is the social security number of every atom. The atomic number. The atomic number. So, what's the significance of this paper? First of all, corrected Mendeleev. Not to say that Mendeleev was bad. Mendeleev was brilliant in what he did, but there were a few things that Mendeleev couldn't account for. So now we know in the post-Moseley world that periodicity, that is the periodic variation in properties, is not a function of atomic mass. It's no longer a function of atomic mass as per Mendeleev, but rather a function of atomic number. Function of atomic number. Okay? And this now resolves the problems with argon, potassium, cobalt, nickel, tellurium, iodine. These three were known. These three were known. And Mendeleev kept saying, go and measure them again. The atomic masses are wrong. Okay? And he was right in certain instances. They did find a number of incorrect values, but these weren't among that group. And lastly, a pair that they wouldn't have known, uranium and neptunium, are in the wrong order. All right. So you say, okay, well, that's cute. But let me show you something else. By understanding that the atomic number is the critical factor in determining where something belongs in the periodic table, he was able to place the lanthanides. If you look on those periodic tables from the early part of the 20th century, they don't know where to put the lanthanides. They're trivalent, so they tend to put them under aluminum, maybe under scandium. They don't know what to do with them. So with this, he was able to place the lanthanides. And more importantly, he was able to predict that there are 14 of them. There are 14 in all. Yeah. Now, how do you do that? It's really simple. Lanthanum was discovered in 1839. Lanthanum was discovered in 1839. It has an atomic mass of 138.91. And there are various other lanthanides that had been discovered. And I'm going to put in lutetium, which had been discovered only recently in 1907. And its atomic mass is 174.97. So what? What can I learn from this about how many elements lie between lanthanum and lutetium? It's anybody's guess. But with Moseley, Moseley comes along and he says, this isn't the critical figure. The critical figure is the atomic number. I'm going to tell you, because we can do the experiment. And we can determine that lanthanum has an atomic mass of 57 and lutetium has an atomic mass of 71. Now, I ask you, how many elements are there? How many elements are there to be discovered? With the atomic number, everything is resolved. In fact, once you know that the atomic number of uranium is 92, you can say with surety that there are 92 naturally occurring elements up to uranium. They couldn't do this before Moseley. And he kept going. He didn't stop with this. Who else was in town in 1913 in Manchester? Niels Bohr. So Moseley looks at these data and he says, I wonder if I can fit these data to a line. So he said, well, Bohr's in the building. I'll go talk to Bohr. And he says, why don't I use a Rydberg-like equation? And this is what he writes. The nu bar varies with the square of the proton number in the following manner. R, the Rydberg constant, 1 over n final minus 1 over n initial, each of them squared, times z squared. But he knew those lines don't all go through the origin. They don't go through the origin. So it's z minus some non-zero constant squared. So wave number goes as the square of the proton number, but there's a little bit of an offset. And this is called Moseley's law. This is Moseley's law. So it's a Rydberg type equation. It's essentially a Bohr adaptation for the X-ray spectra that he had measured. And so, for example, you can have a Lyman-like series. The Lyman-like series would be 2 to 1, right? N equals 2 down to N equals 1. So that means that's all of the K alpha. So the wave number of any K alpha line is equal to, if I plug in 1 over 2 squared minus 1 over 1 squared, this will come out to give me 3/4 times the Rydberg constant times Z minus sigma squared. Well, he keeps going. He keeps going. Let's see what he does. He goes through and he rewrote the thing in a slightly different form, but ultimately if you read the highlighted passage here, hence the frequency nu varies as n minus k squared, and n for calcium is really 20, then k equals 1. He solves for this thing. Huh? Solves for it, and look at this little sort of very delicate, extremely important statement, but very, typical British understatement. There is good reason to believe that the X-ray spectra with which we are now dealing come from the innermost ring of electrons. Oh yeah, from the innermost ring of electrons, because he knows he's way down inside. So sigma equals 1, in this case, for K alpha. For K alpha. And there's a Balmer-like series, Balmer. This is to X-ray what Balmer was to hydrogen, and that would be lines 3 to 2. And if you do, so that would be, by definition, the L alpha lines, and that would be 1 over 3 squared minus 1 over 2 squared, which gives you 5/36 times R times Z minus sigma squared, and it turns out that sigma equals 7.4 for L alpha series. 7.4 for L alpha series. So this is really good. This is really good. Now let's go into the physics. Let's try to understand, what is this sigma? Where does it come from? So for that, let's look at this little cartoon. Here's my K shell. This is K shell. Here's the L shell. Here's the M shell. Now, K shell, I've got maximum, I've got 2 electrons max filled. Okay, L shell, I've got 8 electrons max. And out here, I've got 18 electrons max. Let's look at, first of all, sigma equals 1. That involves transitions from L down to K. So for transitions from L down to K, normally I've got 2 electrons in the N equals 1 shell. If I'm going to have cascade, one of these is missing. There's a vacancy down here. So let's go up here. I've got 1, 2, 3, 4, 5, 6, 7, 8. Now the 8 of these electrons are feeling the positive attraction of the nucleus mediated by the presence of the 1 electron. So you see plus Z minus 1. So we say that the attractive force of nucleus is mediated. Or we say the electron screens the attractive force of the nucleus. So the outer electrons are going to fall down, don't get the full brunt of the positive force of the nucleus. And there's only 1 electron here, so it's, instead of Z, it's Z minus 1. Makes sense. Makes sense. And how about, let's do the next one. The next one would be from 3 to 2. So out here I've got electrons. If they're going to go from 3 to 2, I need at least 1 vacancy. I could have a vacancy here. So there's maybe, instead of 8 electrons, there's 7. Right? Here there's either 1 or 2 electrons. Suppose there's 2 here and there's 7 here. That's 9. Suppose there's only 1 here. Well, 1 plus 7 is 8. But maybe I've blown both of these out. Maybe I've blown more than one of these out. So you put it all together, and it turns out that the number has to be somewhere on the order of, what? 8, 7, something like that. And sure enough, the number is 7.4. So there's a physical basis for the screening factor. The screening factor. Sigma is termed the screening factor. The screening factor defines a Z effective, not the Z. There's a Z effective. It's what's mediated. And to show you, just to get a sense of how powerful Moseley was, here's the thing. I've told you that I've had it drilled into my head that the lambda of copper K alpha is 1.5418 angstroms. There are not many things I know to 5 significant figures. I know my social security number to 9 significant figures, but I know this one to 5 significant figures. And if you use Moseley's law, lambda of copper K alpha from Moseley is 1.546 angstroms. And the delta here is 0.3%. 1/3 of 1%. 1/3 of 1%. There's no question this man should have won the Nobel Prize. No question. He should have won it right away. But he didn't. He didn't. Moseley was very politically active. And he decided when World War I broke out to enlist in the British military. And Rutherford was furious. Rutherford called the Secretary of War and tried to get Moseley a desk job, keep him in London. And Moseley refused. So he ended up in the military. And one of the major battles of World War I was the Battle of Suvla Bay, which was part of the Gallipoli campaign, which was managed by none other than Winston Churchill. This cost Churchill his political capital. It took him years to recover from the debacle of the Battle of Gallipoli. There were, Battle of Suvla Bay took 250,000 lives on the Allied side and about 1/3 lives on the Turkish side. Over 500,000 people killed in that campaign. And on August 8th, 1915, at the age of 27, Moseley was killed in action. And they don't give the Nobel Prize posthumously, so no Nobel for this. One of the most brilliant pieces of work in those early days of the 20th century. Bohr said that World War I, he called World War I a horrible spectacle, inflicting great losses on humanity. But the #1 loss to the world was Henry Gwynn Jeffreys Moseley. So that's why you won't see Moseley's name among the physics Nobelists. Well, this is brilliant work. Is there any data? What's the data? Well, what should this look like? If we take this set of lines and we make a spectrum, spectrum will be intensity, right? Intensity versus some energy coordinate. Okay, so we should have something that looks like this: K alpha, K beta, and then over here, L alpha, L beta. That's what it should look like. And so just to be clear, we have an emission spectrum that is quantized. It's quantized because the energy levels are quantized. So we have a quantized emission spectrum. That's what we should expect to find. It's a function of the atomic number of the specimen. And so we say that this spectrum is characteristic of the target or of the anode. And I told you last day, if I walked into a room and I saw an X-ray spectrum and I saw that this was 1.54 angstroms, I'd go, it's copper. Because as Z changes, so does the element. In fact, look at how sensitive this technique is. It's additive. Look down here at brass. Brass is an alloy of copper and zinc. So there's the copper lines, and in brass, you see the copper lines and you see the zinc lines. So by this technique, I could give you an alloy consisting of 3 elements. And you could see from where those lines are what the elements must be that are present in the alloy. And the relative intensity of the lines must be related to the relative concentrations of the constituents that are present. This is so important. It's amazing. Amazing. All right, so let's look at the data. Here's the data. This is the data for molybdenum. Now remember, this is what we're expecting, and this is what we've got. So there's something else going on here. It looks as though what we have is a combination of. Looks like we've got a combination of this plus this. So we've got, this here is our characteristic spectrum, all right? It's as though our characteristic spectrum is imposed upon something else, and this something else is continuous, right? There's no break in this curve. So this is a continuous spectrum. This is a continuous spectrum. There are various ways of describing this shape. It's certainly asymmetric, but since we're in New England, we call this whale-shaped. It's whale-shaped. And it's got a very steep, it's got a vertical rise here. I want you to note the shape. It's not just arbitrarily drawn. It's a steep vertical rise and then an asymptotic tail. Asymptotic tail. And of course a maximum skewed asymmetrically. So it's not quantized. Not quantized. And furthermore, if you look at this figure carefully, you'll see that there's a family of these. There's a family of these, and they're enveloping one another. They envelop one another, as shown here. So that as the plate voltage increases, the height increases, and the minimum wavelength decreases. So if this is wavelength increasing from left to right, this means that energy is increasing from right to left, which makes sense. As you go to higher plate voltage, you go to higher energies. But what's going on here? What's the physics of this spectrum? Oh, by the way, in the highest one, you see the K alpha, K beta designation. If you didn't know what they were, you just took that value of K alpha, it looks like it's around, about 3/4 of an angstrom by my eyeballing it. It looks like it's about 3/4 of an angstrom. And if you take the calculation of Moseley's law for lambda of molybdenum K alpha, you know that molybdenum Z equals 42 for moly. Z equals 42, plug that in and you get 0.72 angstrom. So that seems to be okay. So in other words, Moseley's predicting the peaks. And the peak, by the way, is, I'm drawing a straight line like this, but in reality these peaks have some finite width because real materials are not perfect, and so there's going to be some variation in the spacing and the energies. Okay, so what's going on here? How can we explain this? What's the underlying physics here? Well, let's take a look. Here's a body-centered cubic crystal, as is molybdenum. So let's say the plane of the table is the anode, and the electrons are zooming in from the cathode in the ceiling. So the electrons are coming down. They're coming down and they're smashing into this, and something's going on that causes the emission of X-rays in all directions. And we've just seen it's okay, that's a good one. You've seen in the central board there what those energies should be, the discrete energies. But let's see what else is going on. I'm going to zoom in at the free surface of the molybdenum. Here's body-centered cubic, and the electrons are coming in. Well, let's say electrons coming in from the top, and electrons charged negatively, and we know that this is net neutral, but there's an electron cloud. And so we've seen Born repulsion in the past. We're going to see it again. The mutual repulsion of the electrons in the molybdenum atom with the incident electron that's just arrived long distance from the cathode is going to cause some repulsion, and it's going to be a deflection. Another electron might come in a little bit closer. If it comes in closer, it might be deflected more. Now, when a charged particle changes direction, any particle, forget charged particle, a change in speed or a change in direction represents an acceleration. But when a charged particle accelerates, that causes emission of radiation. So every one of these changes in direction, change of direction, we term acceleration. And that's point one. And point two, charge accelerating produces radiation because there's an energy change. So What kind of radiation? Every one of these comes off, they give off a photon. And different deflections mean different energy differences. Modest deflections, modest difference. Intense deflection, intense difference. You know, you might even get one that comes in sort of a la Rutherford, that comes in and gets turned around. So what do we see? That could explain what's going on here, where we have at the one extreme, this is very low. This is a high wavelength, low energy. So this is low energy. This is low angle deflection. Low angle deflection. And this is the most common. This is the most common angle. Most common angle. And over here is very high angle, and there aren't many of them. And we can't predict what this line is. There's no way we can calculate that curve except for one point on it. One point on it. And that's the remote possibility that an electron comes in dead on, stops, is captured by the molybdenum atom, and gives up all of its kinetic energy and converts it to photon energy. And that one we can calculate. For that one we know that if we take the energy of the incident electron, the total energy, total kinetic energy is equal to what? The product of the charge on the electron times the plate voltage. The charge on the electron is the elementary charge. And convert that into the energy of the emitted photon. Energy of the emitted photon, which is equal to hc over lambda. If we do that, we can invert this and get the value for this point here, which is lambda shortest wavelength. Lambda the shortest wavelength, which is the wavelength represented by the conversion of the total kinetic energy of the incident electron. Lambda of the shortest wavelength then will equal hc over E times V. And if you plug in Planck constant, speed of light, elementary charge, you end up with 12,400 over plate voltage in angstroms. You know I'm not fond of the nanometer. I insist on using the angstrom in defiance of Système International. So it's 12,400 divided by plate voltage. So you can see that if you have on the order of 10,000 volts, 10,000 volts will give you a shortest wavelength of 1.24 angstroms, smack dab in the middle of the X region of the spectrum. And that's what you're seeing up here. That's what you're seeing up here. There's another term for this phenomenon of changing directions, and it comes from the idea that we're decelerating the incident electrons. Decelerating not by changing velocity, but by changing direction, and it's the German term Bremsstrahlung. Bremsstrahlung. Brems means to brake, as in putting on the brakes of your car. Brems means to brake, and Strahl is the word for ray. Strahl means ray. So this literally means braking radiation. It's the radiation from the braking of the incident electrons. Braking radiation. So the Bremsstrahlung plus the characteristic spectrum give us what we see in the figure up here. Last topic I want to cover is something on instrumentation and safety. Instrumentation and safety. A number of you approached me after the last lecture and asked with incredulity, how could these people work with these generators exposed to X-rays? These were clear glass tubes emanating in all directions X-rays. Well, the answer is it was unsafe, and many of them died as a result of a radiation exposure because they didn't know at the time what was going on. So I want to show you several things that have been done in order to make things a little bit safer and also to be more efficient. And what I'm going to show you is the design by Coolidge in 1913. And Coolidge made the following improvements. And I think I've got a cartoon up here. This is taken from one of your readings out of the supplement. This is out of the Stout and Jensen book. So this is figure 1.5. What I did is I turned it on its side so it would look like all of our gas tubes. Every gas tube I've ever drawn for you has the anode on the right. So just to orient it, I lay it on its side. And so the anode's on the right, the cathode's on the left. And now what I want to do is highlight what the improvements have been. So the first thing that Coolidge did is he used a bona fide vacuum tube. Bona fide vacuum tube. He got the gas pressure way, way down. And this did two things. First of all, there's no glow in the visible. And secondly, it's a much higher efficiency, because when you have glow, what it means is that some of those electrons leaving the cathode are not getting to the anode. They're colliding with gas molecules and consuming their energy. So by the time they get to the anode, they don't have enough punch to kick out inner shell electrons. So vacuum tube is an improvement. The second thing is hot cathode. Hot cathode. What happens with a hot cathode? You know, you have to rip the electrons out of the cathode, and the electrons are bound. So if you raise the temperature of the cathode, the thermal energy then weakens the bonds. And so it takes less coulombic force to rip the electrons out. Now, how's he going to heat the cathode? Let's think about this. You can't use a torch because you've got a vacuum inside. So a torch won't work in a vacuum. So I wonder, maybe if I pass the current, and sure enough, what he does is he's got a second power supply. You see, here's the anode over here. Here's the cathode, and there's the 30,000, 40,000 volts between the cathode and the anode, and the electrons boil off here and zoom from left to right. And he's got a second little circuit here. You can put more than one electrical signal through an item. So let's put a second circuit through here, and this circuit's a little heater circuit. And all it does is it makes this cathode filament, through Joule heating, raise its temperature. And that makes the electrons less tightly bound, and so it's easier to boil them off. So the hot cathode, by raising temperature, reduces binding of the electrons, and you're trying to get rid of them. The third thing he did was water cooling. Water cooling. You've got all of these electrons. They've zoomed across at an acceleration voltage of 30, 40, 50,000 volts. They're crash, 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 hitting that copper or molybdenum anode. Where's that kinetic energy going? Some of it's going into light, and some of it's going into heat, and the temperature of this anode is rising to the point where you could melt this. So what Coolidge did is he put the anode on a hearth, and the hearth is copper, and underneath there's water running through copper tubing. So by water cooling, he's able to keep the anode cool, so dissipate heat. And the second thing, remember Röntgen used pulse power. It was 8 times a second. Bam, 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 bam. If you've got water cooling, now you can go to continuous power. Dissipated heat and allowed for continuous current flow. If you've got continuous current, that means you've got continuous X-ray emission. You don't want an X-ray flash bulb, you want an X-ray beam. And the last thing he did, is probably the most important thing, is he put lead shielding, which I've indicated in yellow. He put lead shielding and beryllium windows. Beryllium windows for efficiency and lead shielding for safety. Okay? Now let's think about it. Let's think about why we would choose these. Why would you choose lead for the shielding and beryllium for the window? For that, I decided, why don't we go back to our friend, the periodic table. Look at where beryllium and lead lie on the periodic table. Beryllium is the lightest practical element. Hydrogen and helium are gases, and lithium as a metal is unstable in moist air. Beryllium is the first metal that can be used sensibly in our atmosphere. And look at lead. Lead is down here. And remember, it's 1913, so forget about the actinides. So you've got bismuth, polonium, and astatine. So lead is effectively the heaviest practical element. Why would you choose this? Why would you choose lead as your shielding? What do we know about the energy levels in lead? First of all, there's lots of them. There's lots of them, because you do not have only K, L, M, and N. You've got N. You keep going, O. So you've got plenty of levels, and the levels are very closely spaced. So if you've got lots of energy levels, and they're closely spaced, then that means when an X-ray comes in, you'll have excitation and cascading down into much, much longer wavelengths. So because of the extra energy levels, this causes the lead to act as a frequency shifter, So it moves you out of the X region. You still get radiation, but it's not so toxic. I mean, you have conservation of energy here, but you don't have things coming at you in the X region of the spectrum. So if there were a shortage of lead, or let's say for the man or woman who has everything, when he or she goes to the dentist, what would be a really cheachy material to make the vest out of? Mercury is a liquid at room temperature. Bad choice. Thallium, toxic. How about gold? How about a vest made of gold? That would work. That would be a classy vest. Now how about up here? Beryllium window. Beryllium is the inverse. Beryllium has very few energy levels, and they're far apart. So that we don't want the X-rays absorbed as they're going through the window. So if you had a window that wasn't crystalline beryllium, you run the risk of losing some of your X-rays, so your efficiency goes down. So you choose a low Z element for the window and the high Z element for the shielding for those reasons. It all goes back to the internal structure, energy levels. Okay. Well, let's take a look at another use of X-rays. X-rays in art. This painting. Anybody recognize this one? The Angelus by Jean-François Millet, painted in 1857 to 1859 on commission for an insurance company in Boston. Millet was very popular with Boston Brahmins because he painted rural life in France, in 19th century France. This painting was commissioned and hung here in Boston. It's now at the Musée d'Orsay. Salvador Dali had to paint this as part of his art education. He hated this painting, and in 1963 it was hanging in the Louvre, and he had the painting X-rayed. He said there's something spooky about this painting. Well, Dali had such authority that he could ask for the X-ray, and they X-rayed it, and they discovered that indeed the painting had been painted over. It's not an art forgery. It turns out that this zone down here, the little basket of potatoes, was not the basket of potatoes in the original painting. The original painting depicted the casket of a baby. This is showing the poverty, the futility of peasant life in France, and these people are so poor that they've just lost their baby. Now you can imagine that this painting comes to Boston, they unveil it, and they say, my God, we can't hang this in the lobby of an insurance company. So my theory is that they sent it back and Millet painted it over and put a basket of potatoes. But their heads are not bowed in the form of saying a prayer thanking God for the bounty, this miserable bounty of potatoes. It doesn't make sense. So X-rays figured out what was going on. So then Dali got a chance to paint, and this is his revenge. This is his painting in 1935. This is Dali, and this is his father. You notice in this case, the man is taller than the woman. Here, the woman is taller than the man. There's all kinds of Freudian stuff going on with where he's got his hat placed, but I don't have enough time to go into that. So you can see what's... while we're talking about Dali, here's the hallucinogenic Toreador. And I want to show you this because it harkens back to crystal structures. He went out one day in Manhattan to buy some Venus pencils. They're pencils, but the Venus was the manufacturer. So you have the Venus de Milo on the pencil box. So you see a bunch of Venuses facing forward and some facing back. Can you see the breast here is the nose of the Toreador. Here's his mouth. Does that help? Okay, those are the gadflies of Saint Narciso, which is, I think, the patron saint of Catalonia. You see here's his cape. And there's the bull. And you can see symmetry planes here. Okay, there's the head of the thing. Okay, there's the bull. Yeah. Okay, now look, here's the symmetry. See, these Venuses are forward. These Venuses are facing backward. What else do we have? I don't know why it's doing this. Oh. Okay, there's the bull. What's the crystal structure of the, see, this is the life force leaving the bull. What's the crystal structure? If you ignore color, it's simple cubic. You can even see symmetry here. You see the shadow of the fly. You see these two atoms here, these two atoms here. There's even something, you see the shadow of the Venus actually looks a little bit like, come on, looks a little bit like this. He really hated this. Okay, we're going to show you one more. We go through this. This is his tribute to Watson and Crick. Over here you have the DNA double helix, and what he's portraying here is that now that we have the capacity to understand how life is encoded, the replication and so on, ironically, humanity hasn't figured out how to stop killing itself. And so he has this group of people all arranged in cubic arrays with muskets pointing at one another. Again, crystallography. You could say, actually, this is simple cubic, but if you put somebody inside, it would be body-centered cubic. And the last thing, lithium. Why is lithium, why is 7-Up called 7-Up? When it first came out, it was called lithiated lemon lime soda. It contained lithium citrate in large quantities. It was supposed to make you happy. It was an antidepressant. And it turns out that some people have a sodium deficiency. Lithium's a smaller ion. If you're already sodium deficient, lithium gets in there, displaces the sodium, you die. So after some tens of people died, they took the lithium out around 1950. So you don't have lithium in your 7-Up today. I'll see you on Friday.